The purpose of grounding in electrical systems is to provide a low impedance path for fault current to return to the source. This path facilitates the operation of overcurrent protective devices such as circuit breakers or fuses, thereby minimizing the risk of electrical shock or fire. Grounding also helps to stabilize voltage to earth during normal operation. There are several types of grounding systems that are employed, including equipment grounding and system grounding. Equipment grounding connects non-current carrying metal parts of electrical equipment to ground. This includes enclosures, conduits, and other metallic components. System grounding connects the neutral point of a power supply, such as a transformer or generator, to ground. This helps to maintain a stable voltage level and provides a reference point for the electrical system. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding electrical systems. It specifies the requirements for grounding electrodes, grounding conductors, and bonding jumpers. These requirements are designed to ensure the safety and reliability of electrical installations. Grounding electrodes are conductive rods, pipes, or plates that are buried in the earth and connected to the grounding system. They provide a physical connection to the earth, allowing fault current to flow safely back to the source. Grounding conductors are wires or cables that connect electrical equipment and systems to the grounding electrode. They provide a low impedance path for fault current to flow. Bonding jumpers are used to connect metallic parts of electrical equipment together, ensuring that they are all at the same potential. This helps to prevent electrical shock hazards. The size of grounding conductors and bonding jumpers is determined by the size of the circuit they are serving. The NEC provides tables that specify the minimum size of these conductors based on the ampacity of the circuit. Proper grounding and bonding are essential for electrical safety. They help to protect people from electrical shock, prevent fires, and ensure the reliable operation of electrical equipment. Failure to properly ground and bond electrical systems can result in serious injury or death. The NEC requires that all electrical equipment be properly grounded. This includes appliances, lighting fixtures, and power tools. Grounding can be achieved by connecting the equipment to a grounding electrode through a grounding conductor. In addition to equipment grounding, the NEC also requires system grounding. This involves grounding the neutral point of the power supply. System grounding helps to stabilize voltage and provides a reference point for the electrical system. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. They work by monitoring the current flowing in a circuit and detecting any leakage current to ground. If leakage current is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity and preventing electrical shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. They provide an important layer of protection against electrical shock hazards. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, or other events. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD are often installed at the service entrance of a building to protect the entire electrical system. Bonding is the process of connecting metallic parts of electrical equipment together to ensure that they are at the same potential. This helps to prevent electrical shock hazards and reduce electromagnetic interference. Bonding is typically achieved using bonding jumpers, which are short lengths of wire or cable that connect the metallic parts together. The NEC provides specific requirements for bonding electrical systems. These requirements are designed to ensure that all metallic parts are properly bonded together. Grounding and bonding are closely related concepts, but they are not the same thing. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metallic parts are at the same potential. Both grounding and bonding are essential for electrical safety. The NEC provides comprehensive guidelines for grounding and bonding electrical systems. It is important to follow these guidelines carefully to ensure the safety and reliability of electrical installations. The grounding electrode system should consist of one or more grounding electrodes. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The grounding electrode should be installed in accordance with the NEC requirements. The grounding conductor should be sized according to the NEC tables. The size of the grounding conductor depends on the size of the circuit it is serving. The grounding conductor should be connected to the grounding electrode and to the equipment grounding bus in the electrical panel. Bonding jumpers should be used to connect metallic parts of electrical equipment together. Bonding jumpers should be sized according to the NEC tables. The size of the bonding jumper depends on the size of the circuit it is serving. Bonding jumpers should be installed in accordance with the NEC requirements. Ground fault circuit interrupters, or GFCIs, should be installed in locations where there is a high risk of electrical shock. These locations include bathrooms, kitchens, and outdoor areas. GFCIs should be tested regularly to ensure that they are working properly. Surge protection devices, or SPDs, should be installed to protect electrical equipment from voltage surges. SPD should be installed at the service entrance of a building to protect the entire electrical system. SPD should be inspected regularly to ensure that they are working properly. Proper grounding and bonding are essential for electrical safety. They help to protect people from electrical shock, prevent fires, and ensure the reliable operation of electrical equipment. It is important to follow the NEC guidelines carefully when grounding and bonding electrical systems. Ensuring a safe and reliable electrical system involves several key components and practices. Firstly, understanding the difference between grounding and bonding is crucial. Grounding provides a path for fault current to return to the source, facilitating the operation of overcurrent protection devices like circuit breakers. Bonding, on the other hand, ensures that all metallic parts of an electrical system are at the same electrical potential, minimizing the risk of shock. Secondly, selecting the appropriate grounding electrode is essential. Common options include ground rods, ground plates, and metallic water pipes, each with specific installation requirements outlined in the National Electrical Code, or NEC. The NEC also dictates the sizing of grounding conductors, which must be adequate to safely carry fault current. Thirdly, the installation of ground fault circuit interrupters, or GFCIs, is vital in areas prone to moisture, such as bathrooms and kitchens. GFCIs quickly detect and interrupt ground faults, preventing electrical shock. Regular testing of GFCIs is necessary to confirm their proper operation. Fourthly, surge protection devices, or SPDs, safeguard electrical equipment from voltage spikes caused by lightning or other disturbances. SPD divert excess voltage to ground, protecting sensitive electronics. Regular inspection of SPD is recommended to ensure their continued effectiveness. Fifthly, proper bonding techniques involve connecting all metallic parts of an electrical system to create a continuous, low-impedance path. This minimizes voltage differences and reduces the risk of shock. The NEC provides detailed guidelines for bonding various components. Sixthly, electrical panels should be properly grounded and bonded. The grounding electrode conductor connects the grounding electrode to the panel's grounding bus. Bonding jumpers connect the neutral bus to the panel enclosure, ensuring a common ground potential. Seventhly, wiring methods play a significant role in grounding and bonding. Metallic conduits and cable trays must be properly bonded to maintain a continuous ground path. Non-metallic conduits require the installation of a separate equipment grounding conductor. Eighthly, electrical equipment, such as motors and transformers, must be properly grounded. This typically involves connecting the equipment's metal enclosure to the grounding system using a grounding conductor. Ninthly, regular inspections of electrical systems are crucial for identifying and addressing potential grounding and bonding issues. Visual inspections can reveal damaged or corroded grounding conductors, loose connections, or improper bonding. Tenthly, when working on electrical systems, it's essential to follow safe work practices. Always to energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as insulated gloves and eye protection. Proper grounding and bonding are not only essential for safety, but also for the reliable operation of electrical equipment. A well-grounded system minimizes noise and interference, improving the performance of sensitive electronics. The NEC is a comprehensive resource for grounding and bonding requirements. Staying up to date with the latest edition of the NEC is essential for electrical professionals. Grounding and bonding requirements can vary depending on the type of electrical system and the specific application. It's important to consult with a qualified electrical engineer or inspector to ensure that your electrical system meets all applicable requirements. The grounding electrode system is a critical component of any electrical system. It provides a low impedance path for fault current to flow back to the source, thereby protecting people and equipment from electrical shock and damage. There are several different types of grounding electrodes that can be used, including ground rods, ground plates, and concrete encased electrodes. The type of grounding electrode that is best suited for a particular application will depend on the soil conditions and the available space. Ground rods are the most common type of grounding electrode. They are typically made of copper or galvanized steel and are driven into the ground to a depth of at least 8 feet. Ground plates are typically made of copper or steel and are buried in the ground at a depth of at least 2.5 feet. Concrete encased electrodes are typically made of copper wire or rebar and are encased in concrete that is in direct contact with the earth. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the electrical panel. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The equipment grounding conductor provides a path for fault current to flow back to the source from electrical equipment. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Bonding is the process of connecting all of the metal parts of an electrical system together to create a low impedance path for fault current to flow. This helps to protect people from electrical shock and prevents damage to equipment. Bonding is typically accomplished by using bonding jumpers. Bonding jumpers are short lengths of wire that are used to connect metal parts together. The size of the bonding jumpers is determined by the size of the circuit conductors. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing in a circuit and detecting any leakage current to ground. If leakage current is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, or other events. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD are often installed at the service entrance of a building to protect the entire electrical system. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding electrical systems. The NEC specifies the requirements for grounding electrodes, grounding conductors, bonding jumpers, GFCIs, and SPD. It is important to follow the NEC guidelines carefully when grounding and bonding electrical systems to ensure the safety of people and equipment. The NEC also addresses the grounding and bonding of specific types of equipment, such as generators, transformers, and motors. These requirements are designed to ensure that these types of equipment are properly grounded and bonded to prevent electrical shock and damage. The NEC also addresses the grounding and bonding of electrical systems in hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. The grounding and bonding requirements for hazardous locations are more stringent than those for non-hazardous locations. This is to ensure that electrical equipment in hazardous locations does not become a source of ignition. Proper grounding and bonding are essential for electrical safety. They help to protect people from electrical shock, prevent fires, and ensure the reliable operation of electrical equipment. It is important to follow the NEC guidelines carefully when grounding and bonding electrical systems. The integrity of the grounding system should be periodically inspected and tested to ensure that it is functioning properly. This includes visual inspections of grounding conductors and connections, as well as electrical testing to verify the impedance of the grounding path. Any deficiencies identified during inspections or testing should be promptly corrected to maintain the effectiveness of the grounding system. The selection of appropriate grounding and bonding methods should take into account the specific characteristics of the electrical system and the environment in which it is installed. Factors to consider include the type of equipment being grounded, the presence of corrosive elements, and the potential for lightning strikes. In some cases, specialized grounding techniques may be required to address unique challenges. Effective grounding and bonding practices are essential for ensuring electrical safety and preventing equipment damage. By following established guidelines and implementing appropriate measures, electrical systems can be designed and maintained to provide a safe and reliable source of power. Grounding and bonding are fundamental aspects of electrical safety that must be addressed in all electrical installations. A thorough understanding of these concepts and their practical application is essential for electrical professionals and anyone working with electrical systems. By adhering to established standards and best practices, it is possible to create electrical systems that are both safe and reliable.